Gatorade flavors. Give an algorithm for how they rank.
Okay, so what you should have done yesterday, it says a rock is thrown upward with an initial speed of 5 meters per second on Earth, and I asked you guys to make a diagram. Check out the diagram, guys. All right, so we've got a rock, and we're going to throw it straight up in the air. Have you ever thrown a rock straight up in the air?
Yeah, but it starts at 0, right? And then you accelerate.
Not if you start it.
Well, we're talking about when it leaves your hand.
Yeah.
Oh.
So I'm going to call that 15 meters per second. And we're going to say, it says that we're on Earth, so we know that acceleration is going to be minus 10 meters per second squared. There's my diagram. Part B says, make a list of given quantities and quantities to find labeled with units in appropriate algebraic science. So what we know at this point is our initial velocity is 15 meters per second, and our acceleration is minus 10 meters per second squared. It's kind of hard to say like what the other things are because they're all dependent on other information.
I wish we had
The mask?
the
Oh, the mass? Well, we're not doing force anymore. We're not going to see mass for a while. Yeah.
What are we measuring?
What are we measuring?
Yeah.
We'll see. It's coming. It's another problem.
Oh,
so what are we going to measure? We're going to calculate some stuff. So it says, what's the acceleration of the rock, guys?
Negative 10.
There you go. Don't overthink it. And then it says, calculate the rock's height after 1 second. So this is giving us a third piece of information so that we can go back and figure it out from our equations. So we have an initial velocity of 15 meters per second. It makes sense that that's a positive value because we're throwing the rock up. Our acceleration is minus 10 meters per second squared. Our time is 1 second. And what we need to find is the height. So our change in vertical displacement, or y. So if we take a look at our equations, the one that Dr. O'Malley typoed is the one that we want. Please change your typoed equations. I'm very sorry. I'm just going to rewrite it on here. A delta t squared. So that's the one that we're going to need to use because it has displacement, initial velocity, acceleration, and time.
Oh, wait. So the equation is velocity initial times change in time plus 1/2 acceleration times change in time squared?
Yep.
Is it changing
We've
time?
seen this equation before, only we had x's in it.
Is it just time or changing time?
Either just
Does
the
it really
same.
matter?
It doesn't
Is
matter.
there a difference?
It doesn't matter. Not really. Because as long as you start your time at 0, the change in time is equal to your total amount of time. Okay, so our initial velocity was 15 meters per second. Our time is 1 second, which makes all of our math easier. Plus 1/2 times acceleration times time squared, which is going to be 1 second squared. So we know this first part is going to give us 15 as our number, 15 times 1, and then the seconds cancel out, so it's 15 meters plus. Then we've got 1/2 times minus 10 meters per second squared times 1 second squared. You guys see what I did? I squared the 1 and I squared the units. And these units cancel. So we're going to end up with meters over here. So we have 15 meters plus 1/2 of minus 10. It's going to be minus 5 meters. So our total displacement here is going to be 10 meters. Should it be positive or negative?
Positive.
Positive, because we threw it up, right? Yeah. Bless you.
So if we threw something down,
Yeah.
would it be, so acceleration would be 10 meters per second?
Your acceleration would still be minus 10 meters per second, but your initial velocity would be minus 15.
So it would both be.
Yep. You just have to be consistent with it.
Oh,
You
yeah,
can make them all positive if
the
you wanted to.
acceleration is reliant on the gravity, it's not reliant on the.
Right. Right.
We're getting case today.
All right, next. Calculate the time required to reach an upward speed of 3 meters per second. So what we're looking at here is at some point, this rock is going to reach a velocity of 3 meters per second in the upward direction. So that's what we're trying to figure out. What we already know is our initial velocity is 15 meters per second. Our acceleration is minus 10 meters per second squared. We're going to use our final velocity here to calculate time. Our final velocity is going to be plus 3 meters per second, and we're trying to find time. You might be able to look at this already and say, oh, this is just the acceleration equation. Acceleration is the change in velocity divided by time. It shows up on our purple sheet as this first one. The change is velocity final is equal to initial velocity plus acceleration times change in time. What do I want to do? Time. How much do you guys like doing algebra?
Indifferent. I'm indifferent.
So do you guys recognize that if we start with this version of the equation, that if we want to solve for time, we just need to switch the acceleration and the time variables? So we've got time equals final velocity minus initial velocity divided by acceleration.
Wait, is that an equation on the front was A equals BF minus BI?
It's this one. Sorry, this one. Where you subtract the initial velocity from both sides and then divide both sides by time. And that's how you get that. But if you get stuck, just look at the front page and there is one there that will work. It's just arranged a little bit differently. So our final velocity here is 3 meters per second minus our initial velocity, which is 15 meters per second, all divided by our acceleration, which is minus 10 meters per second squared. So the difference here is going to be minus 12 meters per second divided by minus 10 meters per second squared. And so we end up with a time of 1.2 seconds. Should it be positive or negative?
Positive.
Positive, yeah, because we're going forward in time and not backward in time. 1.2 seems reasonable. The last one, it says calculate the time required to reach a downward speed of 5 meters per second. Oh, this is handy because we just solved this, so we can just use our equation again. But now what we're doing is instead of looking at it when the ball's going up, we're going to be looking at a point in time where the ball is headed back downwards. And that's why it's going to have a negative velocity. Sorry, it didn't get like small or anything. Because it's now going down. So our initial velocity is the same, 5 meters per second. Our acceleration is the same, 10 meters per second squared. Now we're looking for a downward velocity of 5 meters per second. So because it's downward, it's going to be negative 5 meters per second, and we're going to calculate for time. I'm going to steal the same equation up here. Time equals my final velocity minus my initial velocity divided by acceleration. Final velocity is minus 5 meters per second. Initial velocity is 15. We're going to subtract that 15 divided by minus 10 meters per second squared. So we've got minus 20 meters per second divided by minus 10 meters per second squared, and we end up with a time of 2 seconds. Does it make sense that that's later than the time we calculated in E?
Yes.
Yeah, because it's telling us when it turned around. If we wanted to know how long it was, our rock was traveling upward, what final velocity would we need to use? 0, because it's going to be 0 velocity at the top of that. Yeah. Okay.
So then how would you find the time for like when it goes up and comes all the way back down?
You would double that. So if you, am I drawing pictures? I drew pictures somewhere yesterday. If you're looking at a parabolic situation, you know, like punting a football or kicking a soccer ball or whatever, this time is going to be 2 times the height to the top, because you can't. There's a couple of different ways you can do that. Some of the things that you can assume is that we said yesterday we were only going to be looking at things that were symmetric in shape. So we're always going to have a symmetric shape here. This time is going to be half of the time it takes for it to hit the ground. We also know that at this point our velocity is 0 meters per second. And at the beginning and the end, if we know this initial velocity, it's the same as the magnitude of the velocity on the other side, except for this is going to be a negative velocity. So if this one was plus 15 meters per second, when it hits the same elevation on the opposite side, it will be at minus 15 meters per second. Is it really that bad? I'm sorry. I feel bad now. You don't have coronavirus, do you, Ethan?
I mean, hopefully not.
He's gonna drink it.
Coronavirus.
I mean, we spent 7 hours with each other without our masks off in the past 2 days, so volleyball practice.
We went hiking with the Girl Scout troop and they took their masks off. So those are some of the assumptions you can use with parabolas. We'll talk about that a little bit more in the future because there's some fun problems we'll do. Do you guys have any questions about problem number 2? What?
Are you?
Is anyone in Weedville?
No.
Logan is.
Everyone.
We had to watch a 52-minute video of these people in a French monastery. The whole video was in French, and we had 31 questions about it.
Yeah.
Ethan, it is not
It
that
was.
bad.
It's pretty bad.
It is not that bad.
Then you can drink it. I don't
That wasn't the plan.
Okay, guys. So with problem number 3, they start you out with almost no information. So if you have a diagram of a ball that's been punted, don't worry, if your parabolas are not great, they'll get better. It says that it has a hang time of 3.8 seconds. And so that tells us that here our time is 3.8 seconds. It also tells us that at the peak, the time is 1.9 seconds. We also know that at the peak, the velocity is 0 meters per second. We also know the acceleration, right?
Negative 10 meters per second.
Squared.
Squared.
And so there we have 3 pieces of information, which tells us we can calculate how high this is,
Oh.
right?
That's awesome.
We can also use that to calculate what the initial velocity was when it left the ground. And if we know that, we know what the velocity is where it hit the ground on the other side.
Wait, are you saying wait, so it's just vertical, right?
Yeah.
Okay.
Would you rather me draw the picture vertical?
No. I understand what you're saying now. So it's exactly halfway through when it hits 0.
It's halfway through its travel, so it's going to go up and then come back down. Imagine like this is just time across here instead of like horizontal motion. So when it reaches the peak is going to be at half of the hang time. So it's going to be at 1.9 seconds. So initial velocity. So if we want initial velocity, we would have to have, let's see. Yeah, I'm going to use this first half right here. So I've got 1.9 seconds of time. My final velocity is 0 meters per second. My acceleration is minus 10 meters per second squared. And I want to know what my initial velocity is.
What are we solving for?
Initial velocity.
Oh, we can use the same equation.
Which one?
The EF minus VI over time, or over acceleration over time, or some format of that.
Yeah, only we want to solve for this, right?
Right.
So,
Wait, so we just need to find the.
I don't want to do it this way. This way's
gross.
gross. So if I do final velocity equals initial velocity plus acceleration times time, I'm going to solve for this. So I'm going to subtract acceleration times time from final velocity. So my initial velocity is equal to final velocity minus acceleration times time. Do you guys see what I did? Did I do it too fast? So my final velocity is 0 meters per second minus 10 meters per second squared times time, 1.9. Oh, I put meters and it's definitely seconds. Hmm, 19.
That becomes a positive term.
Yep. But that makes sense, right? That we would have a positive velocity. That's all we have to do for that one. Did it say that? Ooh, graph. Oh yeah, graphs are great. Do you guys remember stacks of graphs?
A little bit. I'll try. It's
I'll try.
oh.
So keep in mind that this horizontal axis is time and not distance. So you're going to throw the rock straight up in the air, and then it's going to come down, right? So when you're calculating this, what's going to happen is you're going to have your highest velocity near the ground and the lowest at the top, and it's going to slow down as it approaches that, which means it's going to change. So we're going to have to do something like this at the beginning, right? Where this is the peak. This is the highest that it gets. So that's kind of an important point. It's a good place to reference. What did we say that the velocity was at the top? 0. So I can like put that right there. There's my dot for that. And we know that it's greatest at the bottom, right? So at the beginning and the end of the motion, here and here is where it's going to have the highest magnitude velocity. What happens in the first half? Is the velocity positive or negative? And is it positive or negative in the second half? Negative. So what's going to happen is this is going to do this thing. You guys remember these? And so this is the slope of this graph. And then acceleration is the slope of the velocity versus time graph. Hello. Thank you very much. So what can you guys tell me about the slope on that velocity versus time graph?
Negative.
It's negative, and it's constant, and it's -10. That's right.
That's crazy.
It's gonna be
I
down
did
here.
not know that corresponded.
Yeah, that's the whole like stacks of graphs thing from what unit was that? Unit 3?
It was a while ago.
It was a long time ago. But the first couple units go really fast. Okay, so you guys got the rest of this? Okay. This is a well-labeled diagram, isn't it? How about this one?
I'd say so. Oh, it says make a list of given quantities and qualities. Oh, no, given quantities.
Well, it does ask, how long will it be in the air before it returns to the thrower?
So we need to find the time.
So what do you know?
We know.
You know the initial velocity and the acceleration.
Mm-hmm. So you know that right here, our velocity is 22 meters per second.
And we-
What's the velocity up here?
You know the final velocity.
It's 0 and then multiply by 2.
Oh, yeah.
0 multiplied by 2.
Like we could.
Yeah,
find the time at
so a good strategy is to just use the front half and then double the time to get to the other half.
That's huge.
Oh,
Wait,
that's crazy.
is B what we did up here?
I feel so stupid.
Yeah.
So we are.
You didn't draw a motion map.
Oh, okay.
Remember
I
motion maps?
just read velocity and acceleration map,
And you read graph. Yeah, that's when you're gonna do the like dots thing. I would do it like this though.
It's 0 per second.
And if you know how many seconds it takes to get to the top and you know how high it is, then you can mark that. You can mark the height on your motion map and then you can put the correct number of seconds. It can be very quantitative. I'm sorry I ruined your Gatorade. I feel bad.
I already drank half of it, so I don't feel the full one.
I only ruined half of it then, I guess. I still feel bad.
But you gave Charlie a full Gatorade, so
Yeah.
you should feel good about that.
So your net Gatorade.
Yeah,
Gain
technically your
plus
net Gatorade
one
is up one.
One half.
Or yeah, one half. That's what I meant.
Fascinating.